Hi, I'm David, and for this workshop, I want to talk about two recent projects on robustness. First, I want to talk about robustness against adversarial examples. Specifically, I'm going to present confidence-calibrated adversarial training, which allows to obtain robustness against various types of adversarial examples, even if unseen during training. And second, I want to talk about a very applied problem of robustness, namely robustness against bit errors in quantized DNN weights. In the context of DNN accelerators, robustness against such bit errors can improve the energy efficiency significantly. So this first part on confidence-calibrated adversarial training is joint work with Matthias Hein and Bernd Schiele. In this paper, we address the problem of robustness against adversarial examples. While adversarial training usually focuses on robustness against one specific type of adversarial examples, for example, L-infinity ones, we also consider robustness against various other threat models. Training on adversarial examples can usually be formulated as a min-max problem. Here, the outer minimization problem learns the weights, and the inner maximization problem computes adversarial examples. Here, as highlighted in red, we consider L-infinity adversarial examples. Overall, adversarial training tries to minimize the cross entropy on these adversarial examples, which means that we want to have high confidence predictions on adversarial examples. As can be seen, the model learns to predict the correct class in blue with very high confidence within the L-infinity ball, which is highlighted in red and is 0.03 on SVHN here. And this is visualized by plotting the confidence in the correct and the potential adversarial class along a specific direction in input space. However, the obtained robustness does not generalize to larger L-infinity perturbations, as shown here. Adversarial examples can easily be found right beyond the epsilon ball and can also achieve very high confidence, as shown using the pink line. Similarly, training on L-infinity adversarial examples does not generalize to other threat models. Here, this is shown for L2 adversarial examples. As before, high confidence adversarial examples can easily be found with comparably low L2 norm. Overall, by enforcing high confidence predictions on adversarial examples, adversarial training is unable to generalize robustness to unseen threat models. And we think that this is because extrapolating high confidence predictions beyond the epsilon ball used during training is not meaningful. Instead, the model should somehow reduce its confidence when entering regions of the input space that are unknown, including adversarial examples. Our confidence-calibrated adversarial training encourages the model to yield low confidence predictions on adversarial examples within the epsilon ball during training. And this is illustrated here. The model quickly resorts to a completely uniform prediction when perturbing the clean training example, which is shown at 0 in the middle. And this behavior is extrapolated beyond the epsilon ball that is actually used during training. After training, robustness is then obtained by rejecting those low confidence adversarial examples. On SVHN, for example, we chose a confidence threshold of 0.6, and we are clearly able to reject the majority of adversarial examples as shown in the confidence histogram on the right. For the model to actually assign low confidence to adversarial examples, training can be summarized as follows. First, however, it's important to note that we train on both clean and adversarial examples. Then these adversarial examples are obtained by explicitly maximizing the confidence. Specifically, we maximize the confidence in any but the true label, which is marked in red here, where f sub k denotes the predicted confidence in class k, and we take the maximum over all classes except for the true class y. Using the computed adversarial examples, we compute a new target distribution as illustrated below. In particular, we consider a convex combination of a one-hot distribution on the left side and a uniform distribution on the right side. And thereby, we explicitly model how the model is supposed to transition between high confidence and low confidence. And as shown in the plot, the transition follows a power function. As a result, the transition happens very quickly and close to the clean training example. And at the border of the used epsilon ball, an entirely uniform distribution is used. And this deep transition is important in order to bias the network towards extrapolating this uniform prediction beyond the epsilon ball. After training, robustness is obtained by rejecting low confidence adversarial examples. And note that this is in very stark contrast to adversarial training. Usually, it's very easy to find adversarial examples against our confidence-calibrated adversarial training, but it's hard to find high confidence ones. And as can be seen here, the network is able to approximate the chosen target distribution on the test set very well. The transition from one-hot to uniform distribution happens very quickly. Furthermore, the uniform distribution is extrapolated beyond the epsilon ball as intended. And as a result, even if the class label changes along this direction, the adversarial examples can be rejected. And this way, we obtain robustness against larger L-infinity perturbations. This also generalizes to other threat models. Here, this is shown for an L2 attack. However, I will also show results for L0 and L1 attack as well as adversarial frames. We also think that biasing the model towards low confidence predictions is in unknown areas of the input space is a desirable goal in general. Here, for example, we show the confidence of the model along an interpolation between two test examples, a 2 on the left and a 7 on the right. And on the top, adversarial training will always yield high confidence predictions. And this is shown especially for the pink line in the middle, where adversarial training gives a very high confidence to this combination of a 2 and a 7. Our confidence-calibrated adversarial training on the bottom, in contrast, results to uniform distribution as it is trained. And I think this is significantly more meaningful to assign low confidence on these examples that are kind of unknown and that clearly do not belong to the data distribution. So in summary, our confidence-calibrated adversarial training enforces low confidence predictions on adversarial examples. And then in the second step, we are able to obtain robustness by rejecting these adversarial examples. Because this behavior is extrapolated beyond the epsilon ball used during training, robustness also generalizes to new threat models. Before presenting actual results, I briefly want to talk about a proper evaluation. We all know the standard robust test error is usually computed as the fraction of test examples that are misclassified or can successfully be attacked. So the robust test error also subsumes the clean test error. And as can be seen here, unfortunately, our model does not seem very robust. The robust test error is nearly 100%. However, if we look at the confidence histograms for adversarial examples, there's a significant difference. On the left, for adversarial training, we will see that most adversarial examples receive high confidence, most of the successful adversarial examples plotted here. And on the right, however, our confidence-calibrated adversarial training assigns low confidence to most of the adversarial examples, so these could be rejected. And that's what we do. So we propose a confidence threshold with robust test error that takes that into account. Again, this is the fraction of either misclassified test examples or successfully attacked examples. But additionally, they have to pass the confidence threshold. And on the left, we can see that this confidence threshold robust test error also benefits adversarial training. However, the improvement is rather small here, 1.3%. And this is in stark contrast to our confidence-calibrated adversarial training, where more than 58% of the adversarial examples can be rejected. And as a result, we outperform regular adversarial training. And here I want to emphasize that this confidence threshold robust test error is completely comparable to the standard formulation in related work. So it remains to determine this confidence threshold. And obviously, we want a confidence threshold independent of adversarial examples, and we want to reject as few clean test examples as possible, because rejecting too many clean test examples is obviously unacceptable in applications. So we decided to fix the confidence threshold at 99% true positive rate. And here, true positives are the correctly classified clean test examples. So we want to reject at most 1% incorrectly correctly classified test examples. So on SVHN, we report the worst case confidence threshold robust test error, considering 7 different white and black box attacks, which actually maximize the confidence in order to appropriately attack our models. And regarding the L-infinity adversarial examples used during training, we slightly outperform adversarial training. However, this is not the main focus of our work. Instead, I will also show results for 4 unseen attacks. Here, these are larger L-infinity perturbations, L2, L1, and L0 adversarial examples. And all of these cases are very successful against the regular adversarially trained model. L2 and L1 attack achieve nearly 100% robust test error. Our confidence-calibrated adversarial training, in contrast, generalizes robustness significantly better to these new threat models, reducing, for L2, for example, 100% robust test error to roughly 30. These results are confirmed on Cypher 10. Here, our model performs slightly worse on the seen adversarial examples and on large L-infinity adversarial examples. However, on L2, L1, or L0 adversarial examples, we significantly outperform adversarial training, so that the robustness generalizes to these threat models again. For L2, we reduce the robust test error from 100% to nearly 50%. Confidence-calibrated adversarial training also generalizes better to unconventional threat models. So for example, on the left column, we consider adversarial frames, where we also outperform the baseline. In the middle, we consider distal adversarial examples. These distal adversarial examples are computed to maximize the confidence on random noise images within a small epsilon ball, which we can perfectly reject with our confidence-calibrated adversarial training. And in the last column, we show that we also improve performance on corrupted examples, as shown on Cypher 10C. Finally, we found that confidence-calibrated adversarial training also improves accuracy, especially on Cypher 10 on the right. The improvement is significant, both with rejection and without rejection. So with confidence thresholding and without. Especially with thresholding on the right, we obtain a test error of 6.7%, which outperforms both normal training and adversarial training. So overall, I presented a new approach based on adversarial training to obtain robustness against various different threat models. And to this end, we train a model to assign low confidence to adversarial examples. And by extrapolating this behavior beyond the epsilon values during training, we also obtain robustness against previously unseen attacks. And additionally, we found that accuracy improves, and we also test our model against various unconventional threat models. So if you're interested in the work, check out the webpage or get in touch. So in the second part of the talk, I want to shift gears a bit. I want to talk about a very applied problem of robustness, specifically robustness of quantized DNN weights against bit errors. And in the context of DNN accelerators, this can be shown to improve energy efficiency. And this is joint work with Nandini Chandramurthy, as well as Matthias Hein and Bernd Schiele. So DNN accelerators usually feature a large portion of on-chip SRAM or on-chip memory in general, and these are used as scratch pads in order to store weights and intermediate computations. And data access and movement usually makes up a very significant part of the energy consumption of those accelerators. So reducing the voltage of the memory of the SRAM in this case has become a very interesting direction in order to reduce energy consumption. So as shown here, energy consumption per SRAM access on the right can be reduced significantly at lower voltages. Note that both axes here are normalized by Vmin, which is kind of the lowest measured voltage for error-free operation. Unfortunately, these SRAM arrays quickly become unreliable when reducing voltage. And this is illustrated here for two voltage settings. These maps show the bit error probability per bit cell for a small portion of the SRAM. And as you can see, the rate of bit errors increases very quickly when reducing the voltage. Yeah? And in practice, this will obviously directly affect DNN accuracy because the DNN weights are changed. So in fact, it can be shown that the bit error rate actually increases exponentially. This is shown in blue. Note that the left axis is in log scale. And this means that the DNN has to endure exponentially increasing rates of bit errors in order to reduce the voltage and the energy consumption. Unfortunately, this results in a significant drop in accuracy. In this plot, we show the robust test error for a specific bit error rate. The robust test error here is the test error computed after injecting bit errors in the weights. And note the change in axes. We have now on the x-axis the bit error rate in log scale, and on the y-axis the robust test error. Note that the robust test error increases very quickly, even for very small bit error rates for this 8-bit quantized, normally trained model on Cypher 10. So we consider a very simple but realistic bit error model. We assume that bit errors are distributed uniformly across spatial locations, while in practice for a fixed chip and a fixed voltage, these locations are assumed fixed. They can be assumed random across different chips. Also, these bit errors at higher voltages, meaning lower bit error rate, are usually a subset of those at lower voltages, meaning higher bit error rate, as shown on the top here. Based on this model, we propose a combination of 3 methods to improve robustness. First, a robust fixed-point quantization, then weight clipping during training as regularization, and finally, training on random bit errors. In contrast to related work, our approach generalizes across chips and voltages, which allows to reduce energy consumption with little to no increase in the test error. So compared to standard fixed-point quantization, we reduce quantization range and study the impact of implementation details. And we actually found that these implementation details are rather important to obtain robustness. And as a result, as you can see here in the brown curve, the robustness is improved. However, for high bit error rates, robust test error still increases quickly. Second, we use weight clipping during training. This means that during training, we constrain weights to a small interval using projections. And we found that this regularizes the DNN to learn more redundant weights because the network has to use more weights in order to produce large logits, which will minimize the cross-entropy loss. And this redundancy introduces robustness in the weights. And this is shown here in the blue curve. Especially for high bit error rates, the robust test error is decreased significantly. Finally, we combine weight clipping with random bit error training. Here we inject completely random bit errors during training to further improve robustness. Note that this comes at a slight cost of an increased clean test error, which is shown on the left at 0. However, the robustness is improved significantly for high bit error rates. So note that the increase in robust test error is, for example, here below 1% for a bit error rate of 0.1%, roughly. And as marked in red, this already enables a reduction in the energy consumption of roughly 20%. And of course, higher energy savings are possible with a slightly larger increase in the robust test error. In black, the lowest robust test error achievable for each bit error rate is shown. I note that for low bit error rates, robust quantization and clipping is enough. For high bit error rates, we need random bit error training. And our approach also is applicable to low precision models, here for a 4-bit quantization, for example. And this allows to have the advantage of for a low precision quantization, which also saves energy, and low voltage operation, which further saves energy. So in conclusion, we consider a uniform bit error model that realistically captures low voltage operation. We propose robust quantization, weight clipping, and random bit error training to improve robustness. And we also, in the paper, for example, show that our approach is able to generalize to real profile bit errors, even if these bit errors deviate significantly from our model, as shown on the top right here, where the bit errors are strongly aligned along columns. You can find our paper on arXiv, and again, get in touch or feel free to ask questions.